Hello, everyone. So today we're going to take a small detour from the very great technical presentations that we've seen today and dive more into combining chemical engineering with bio and electrical engineering as well. So my main focus with my presentation and AIChE is based in the alternative protein industry. So we know that we have all different kinds of alternative proteins now. We have burgers made out of soy, we have burgers made out of beets, we have all these other kind of things. But what if I told you we can make things out of bacteria? Well, that may sound kind of harmful and dangerous. When you think about it, bacteria outnumber, well, within our own bodies, much more in the real world, but within our own bodies, bacteria outnumber us 10 to 1. If we could use bacteria, which are extremely abundant on Earth, we can make plentiful food sources from them if we have the right technologies. So, my clinic presentation will be on AIChE, which is basically what we're trying to do here is we want to utilize pulsed electric fields to improve the precision fermentation process so that we can then apply that to the alternative protein industry. Now, I have bolded two terms up here, pulsed electric fields and precision fermentation. What do these two mean? So, fermentation is very familiar to chemical engineers. However, precision fermentation takes a slightly different route. It is not the same as traditional fermentation where we consume the product that we create, but rather we are treating the cells so that we can use them as factories to collect their byproducts for further use. So we're taking our fermentation processes that we know and applying them to a much smaller scale. So what we do is rather than making a product, we make more of the byproducts. And so the broth is really what we're focusing on. We're not focused on the bacteria we throw in. We want what they can produce for us. So the next term, pulsed electric fields, this is basically a way of saying we're shooting electricity through a medium and through our cells to change their composition, to create pores in them, let them expose more of their byproducts, as well as to increase their proliferation rate, and so essentially their growth rate. And so, as you can see from the diagrams below, we would put our cells in a small cuvette, send our electric currents through them, and depending on the current, the voltage, and all of that, would have different effects, which is a main focus. So, while many of the great presentations today had a lot of technical work and a lot of numbers, ours is in the very beginning stages, and so we're first working towards our proof of concept, which is how exactly do E. coli respond to pulsed electric fields? And so we're focused, because of what we want to do with alternative proteins, we're mainly focused on their extraction and their proliferation. So the problem with this is there is very limited literature on how pulsed electric fields affect E. coli. And so our first goal is to look for the thresholds, because this pulsed electric field process is actually used in vegetable sterilization for your normal produce. But that's taking it too far. We don't want to kill the E. coli. We want to increase their growth rates, increase their byproduct production. That's our main goal. So we need to find threshold values where we don't kill the E. coli, but we also don't want it to have no effect at all. And so once we have this, our end goal is we want to develop novel equipment with what we observe, and then apply it to, again, the precision fermentation industry as well as the alternative protein industry. And so these pictures right here, we were previously experimenting with Trichoderma ricci, or T. ricci. However, it was way too filamentous, and it wouldn't really work with what we wanted to do. So that is why we switched. So where did this come from? Why are we doing it? The creator of AIChE, who is unfortunately not here today, wanted to combine activism with engineering, and so we wanted to support the companies who make all these products for people who don't consume animal products, and so give them equipment to help reduce costs and increase their productivity. And according to Perfect Day, which is one of the companies that we were inspired by, their animal-free processes are very, very beneficial to reducing the world's hoof print. And so, as you can see by the numbers, their processes consume significantly less water, less land, produce less greenhouse gases, and consume less energy than typical processes. So here's our team, and I'll be giving a general overview of everyone's role on this team. We have the biochemistry team, electromechanical, and the entrepreneurship. And within all the members of this team, everyone has very specific roles. However, we are also very intertwined in basically every aspect of this project. So, biochemistry team. This includes cell culture, fermentation, and analysis. And they're really descriptive, and they basically tell what they do. But so cell culture team, basically responsible, they are step 0. In order to do our experiments, we need cells. And so cell culture team is responsible for culturing E. coli plates and getting us everything we need to get this project going. Fermentation works with the fermenter and maintains our stock cells and solutions. So we have a good quantity anytime we want to take tests and measurements, keeps them running, and so they don't cause an overgrowth and get past saturation. Analysis team is more so once we've established our pulsed electric fields work, and we're going to give our cuvettes to them to test, okay, we pulsed it at this much, did our protein production increase, did anything decrease, are the cells dying? That's the kind of things we need to know. Moving significantly over, to the electromechanical team, they're working more on the novel equipment type aspect of this, because again, we need both a proof of concept if we want to get to our final goal of equipment. And so mechanical team, mainly designing external chambers of the reactor. I know I was updated recently that we've established a really good flow chamber, and we're now just looking to implement the electromechanical side with the AIChE team, who have been doing work on that, which I'll get to. COMSOL modeling, this team has really been looking at both flow rates through the channel we've been designing, as well as the electrical flow through the channels as well. Electrical design team, again, they've been interfacing a commercial electroporator, and I was updated actually recently that we have established a good design for that, and we're ready to move forward with implementing it into our actual chamber that we've created. And then entrepreneurship team has been very hard at work, especially during this time, and they've been constantly applying to grants and getting funding and managing all the LMEET budget and playing a very essential part in keeping this team running. So what have we done? Major accomplishments this year and last year, we were using TREC initially, and we conducted many experiments with it. So pictured in the left is our fermenter. When we first got it, we had to make some slight modifications, and that's with it with all the ports not attached. But it was working very well then. Had some issues, but they were fixed. So in the center here is our TREC, and as you can see, it was incredibly filamentous. This was even when it was diluted, which was a problem because if we wanted to put it through a small flow chamber, through an electroporator, it would definitely get clogged. And so as you can see in the flasks above, the way it was growing was not ideal for what we wanted it to do. And we initially chose TREC because that is what Perfect Day was using, but with the equipment we had and the way we wanted to do it, we didn't see it as being beneficial, and so we switched to E. coli. And then pictured on the bottom right over here is basically the whole setup of the fermenter. On the left is just the chamber, or not the chamber rather, the fermentation unit itself. And so we got to work with that and reattach it to have it do what we needed it to do. For the mechanical team was very hard at work, but a lot of it was trial and error. So we got this very good design for our chamber, and so basically, as you can kind of see by both models on the left, the small hole in the middle is where our cells would be pushed through, and the two plates on top would be the electrodes for electroporation. And so as they're flowing through, we would send our pulses through, shock the cells, and have them continue on to the next stage of the experiment. In the center here is from the electromechanical team. They were working on making custom wires, and they were also working on making a custom electroporator. However, we abandoned that idea only because we didn't have the equipment we wanted, and the complexity of having it to do it with only the materials we had wasn't ideal. So now we were interfacing a commercial one and attaching it to our normal system. And on the bottom right here is the COMSOL modeling. This one is a flow rate one, and so if you kind of picture this diagram with our COMSOL, or with our 3D printed models, we would have the ports coming from the top, going in through this thing, in through the channel and coming right back up. And again, entrepreneurship team was very hard at work applying to all of these grants this year, and we've gotten a lot of experience by going to them, and we also got accepted to the new venture competition at Rowan, which is very exciting. And so we're really looking forward to that. All right, and so, like I said, moving forward, we have transitioned to E. coli. Our main goal is to get more electroporation data going, to actually run some testing, which we've already started. And the main target, and why I included the growth curve here, is because we're working with a very small window. We want to get our cells to saturation, which is stage 3. Once they're at saturation, we can dilute them down and conduct our experiments. And as we conduct them over a span of about 16 hours, we're seeing if, okay, we shock them, we get what we want. Now we're going to see, are they coming back to saturation? Are they still alive and functioning? And so these other pictures are basically our transition stages to E. coli. I want to thank AIChE for hosting this amazing event, as well as NJIT for having it here. And a special thanks to our leader of LME, Scott Chang, who unfortunately couldn't be here, and everyone involved on the LME team.
Thank you. So you are shocking those E. coli with the electric field. How do you pick the parameters? I mean, there's a voltage, duration,
Yes.
frequency, all that.
So currently, we have found several sources that have really good parameters. And so for our proof of concept right now, my team, I'm on cell culture team mainly, but we're working towards, okay, we're going to run our own tests at these same parameters and see what we find as well. So right now, we're modeling what we're doing after another study. And so I think what we're doing right now is we're testing 0, 1, and 10 pulses at certain voltages. I don't remember off the top of my head. So we're running basically by the time it's done, a 27 grid test of that, meaning voltage by pulse.
And the concentration of this flow that goes through this cell, how do you pick the concentration of cells in the fluid?
That's what the design team has been working on, actually, because when we're doing our small-scale testing, we've been diluting it by hand each time, which obviously we can't do if it's inside the equipment. And so I believe we were going to run it in a way where it's a very good question. We were going to run it in a way where we could get the concentrations we needed for basically a small semi-batch reaction where we would go through, and once we establish, okay, it functions well at these concentrations, but we get our maximum production here, and then we're going to modify it based on what we find. We're very much still in the experimental stages, especially when it comes to equipment, because we haven't actually made our system yet.
Regarding the colorful images with the CFD console, can you go back to that
Sure.
real quick? If I don't make a comment about that in every possible scientific meeting, I feel uncomfortable. So I'm seeing beautiful, colorful images there. First of all, what was the purpose of doing this modeling? What are you trying to extract from this to be able to use it in your design? What was that flow parameter that when you find it, it will be usable?
Right, okay. So we were modeling, I also wanted to include the COMSOL team was still working on their electric field model for COMSOL, so unfortunately I don't have that one. That's the one I wanted to put in as well. So we tested flow first because we've had many equipment issues in the past, and so we wanted to ensure that this flow rate would be sufficient enough so that we wouldn't cause clogging, we wouldn't cause any kind of leakages with what we have. And so that's why we just started with the basis of what we know. We're we know how to model flow rate. Let's see what happens when we put it through the chamber. And so this is also where we were kind of looking at, do we want to have a square design for our tubing, or do we want to have completely circular tubes? So as you can see here with the minimized flow rates in the corners, that's how we were kind of deciding our basic modeling, because again, it doesn't have a lot of use right now, but it was mainly, we were just starting to model, and we're okay, this is how it's going to function. Now we need to start with electric field. What about clogging? What about this? So that's kind of where we were going with a basic model to start.
I see some blue regions there. I'm sorry, teach me a little bit. So why there is blue there near the walls?
So I believe this is the flow rate model. So there is blue there because the way that this console model is designed, it's completely square, as in like the entrance ports have right angles. So as the flow goes in, I believe it hits a turbulent flow in those corners, and so it drops the flow rates there. And so.
So do you think that this is nothing to do with the walls not moving?
No, yes, that as well. Again, I don't believe you can model, you might be able to, elastic type materials in COMSOL. I'm sure you can, but we haven't gotten to that stage yet. But it definitely is the way that the model has been set up. Granted, this will not be a completely stationary system.
Thank
so.
you.
All right, thanks.
Hi.
2 short questions.
Mm-hmm.
So I followed everything, I think, but except for one part. So you apply these electric fields to the bacteria and break the cell wall, and
Yes.
then what
So,
is different here than like killing them?
yes, okay. So what we want to do is we don't want to kill them, and we don't want it to
Right.
have no effect. We want to break up the cell wall so that they increase their production rate, and that's again why we wanted to do this at saturated. So at saturated, and when it's getting close to saturated, protein production is highest. So when we shock the cells at this, they're suddenly damaged, they need to repair. So they stay stuck in that stage for a while and continue to produce them. Not only that, but now that they have pores in them, they are also producing more proteins as well.
Right.
So that's
okay.
why finding that threshold was really important. So we don't want to kill them, but we want them to release more of what their byproducts are.
Okay, that makes sense. I think that's where I felt, I got disconnected. Okay, and what does element mean? Electric meat or
So
something?
Element was the name created by the creator of Element, and basically to kind of play on words, the electroporation and the idea of alternative meats and alternative food products.
All right, thanks.
Have to thank you.
Sure, thank you.